Okay class, in this lecture we will see what is specific heat capacity in case of solids and how the first law of thermodynamics deal with solids, and then we will see the atoms in the crystal structure, they are coupled and how they give rise to different mode of vibration. Then we will see using first law and including the concept of specific heat capacity, the change in internal energy of the atoms, and then we will see what are the experimental facts and the coupling of atoms in the crystal structure, that is of particular importance because it will give rise to different theories regarding specific heat capacity of solids. Okay, so class, let us start with specific heat capacity. I am writing it in short. So class, this is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 Kelvin, I will say. Okay class, so this is specific heat capacity, and if I define heat capacity, it is the same thing. Okay, but here in specific heat capacity we define the unit of the substance, the unit of the mass, amount of the substance. Here if it is 1 gram, then it is specific heat capacity of that particular substance. And if we talk of heat capacity, then we have any arbitrary amount of substance. Okay, and to raise the temperature of that amount of substance by 1 degree, that is the heat capacity. And if we write specific molar heat capacity, okay, here I have specified again the amount of substance, it is 1 mole. So how you will define molar heat capacity? It is the amount of heat required to raise the temperature of 1 mole of substance by unit interval, or I will write 1 degree Celsius. So this is the definition. Now we see, if you provide heat energy to a substance, then what will happen? What will be the changes in the substance? Okay, so the changes we can see with the help of first law of thermodynamics. So you are well known with the units of specific heat capacity and molar heat capacity. I am not going with them. And here the first law of thermodynamics states that if you give some amount of energy, first law of thermodynamics, it states that if you give some amount of energy dq, heat energy, to a substance, it is used in two ways. One is to raise internal energy of the substance, and to do mechanical work. Okay class. So if you write it in equation, then you can write the amount of heat energy given to the substance increases the internal energy. U is the internal energy and PdV. This is mechanical work. Okay class. So here you will see the internal energy is sum of different kind of energy, potential energy and kinetic energy of the particles which are present inside the particle. Okay, and you can take idea of the internal energy from the temperature and the volume. Okay class. So here you need to come out of the nest which you have created in 12th standard, that internal energy is purely a function of temperature. So this is not right thing. Internal energy is also function of the volume. So I am writing it here. So change in internal energy depend upon two parameter. One is change in temperature and another is change in volume. So now come to this another factor, that is the mechanical work. The mechanical work can be controlled mechanically, or you can, if you specify some condition, it can be controlled by specifying condition. Suppose particularly in case of solids, if I take the volume remains constant, then what will be the change in the volume? This will be 0, and the mechanical work, this must be equal to 0. So from here you can see, in case of solids, the amount of heat energy given to the solid is utilized to increase the internal energy of the solids. So here I will write it that for solids V is constant. So the heat energy given is equal to internal energy. Okay class. And if you find the specific heat capacity, then it also specific heat capacity C, it can be measured at constant pressure and at constant volume. Okay, in case of solids the volume is constant, so we will go with specific heat capacity at constant volume. As you have seen, the amount of heat energy given to the solid increases its internal energy, because the mechanical work it is kept 0. So the specific heat capacity CV, this will be equal to dq by dt, okay, at constant volume. This is equal to du by dt at constant volume. Okay class. So this is specific heat capacity in case of solids. Now come to this thing, and the change in the internal energy, we will see it here in detail, and we will make use of this knowledge in the coming lectures. You see, you have seen that in the crystal the atoms are coupled. You need to keep it in mind, because all these things will help you to solve, to remember or to learn different theories. Okay, so here the atoms are coupled, and how this coupling will impact the mode of vibration, you need to understand it. So I am making here coupling Oh, sorry. Firstly, come here. This energy, heat energy, will increase this internal energy. Heat energy will change the internal energy. Okay. So this internal energy change can be written in terms of the kinetic energy plus potential energy if I write it UP. Okay. Now we have seen in the crystal that this is one atom and another atom is here, and these are coupled with each other with a bond, and I am representing the bond with the help of spring, and let the spring constant here is K. Okay class, mean to say the force is equal to minus Kx, and you have done this in 11th standard. Minus sign is here because the direction of displacement and the restoring force developed, those are in opposite direction. Okay class, so here two atoms are there, A and B, which are at the lattice points. Okay, so what will be the, due to this change in internal energy, there will be change in the potential energy, and that change can be written like UP, this is equal to 1 by 2 Kx square. You have done this in 11th standard. And what is K? What is this K? How it is related to the frequency of a vibration? This is K by M, where M is the mass, and this is equal to omega. I will write it like this. Okay class. Okay, so this energy is equal to half, you solve it and you will get mass into omega square into x square. So class, this is what? This is the internal energy. Oh sorry, internal potential energy. Okay, for this thing. And if these particles are moving about their equilibrium position, and where the equilibrium position is, the equilibrium position is corresponding to the lattice points inside the lattice structure. So the kinetic energy UK, this will be equal to P square by 2m. I am writing here P, and this P is the momentum gained by the particle due to this energy. So this can be written like 1 by 2 into m, mass, and the velocity, instantaneous velocity of the particle placed at the lattice point. So this internal energy is combination of, this change in internal energy is combination of internal kinetic energy and potential energy. Okay class, now we need to see that other atoms are present because the crystal arrangement is a long range arrangement. So this is not only a single spring here. Okay, so if it has been a single, we have only two particles and there is one bond only, then we can say that the frequency will be omega, a single frequency. Okay, and see the arrangement of particle along this direction, let it is at a distance a. Okay, I am taking this distance, or you can say the length of the spring is a along this direction. So other particle which is present here, it is again at a distance a, or I will say the length of the spring in this direction, it is again a. Okay, but you see, it is not necessary that in other direction the particles are arranged at the same distance. So if I take the particle at this distance, so along this direction the particle are at high distance. So here you will see the bond length here, or the length of the spring, it is different. Okay class, so here let I take this value to be Ka. So in this case, if this distance of the particle or arrangement of the particle along the vertical direction is at a distance b, then here the value of K will be different, let it is Kb. So this is how you can see the coupling of the atoms impact. Okay, if the particles are at the same distance, then I can write that this distance is A and here K will be Ka. But due to definite arrangement of the particles, okay, which may be different but it is periodic, so all are crystal. Okay, so arrangement of particle or coupling of the particle along different direction will give rise to different mode of vibration. So class, from here, from this discussion, one thing is very clear in our mind, that in crystal there is not only a single mode of vibration. The particles along different direction maybe or at different lattice points will be in different mode of vibration. So this is the thing what I want to tell you here. So we have seen how the internal energy changes. Now we will see what the experimental facts say. So class, we have less time and I have noted down the experimental facts. You need to cram these because we can't do experiment, but we will see them in details in theoretical part because you do theory. So the experimental facts say that at room temperature, at normal temperature or at high temperature, the CV, specific heat capacity at constant volume, that is for solids, it is found to be constant and that is equal to 3R. If you put the value of R, then you will get 5.96 calorie per mole per Kelvin per degree Celsius. Okay, and you see here is no any temperature, so CV at high temperature is independent of temperature. ये याद रखना है. Okay, and you can see here that at high temperature CV curve for CV and T, it becomes flat. If you increase T further, there will be no any increase in CV until the substance remains solid. Okay, its phase do not change. Now the another important point here is at a low temperature, mean to say when T approaches to 0. Okay, so the behavior of the curve, you can see CV decreases with the decrease in temperature and finally it meets to 0. So this is what we obtain experimentally, and here for different materials the behavior of the curve is different. It follow T cube law, mean to say CV is directly proportional to T raised to power 3. You see at high temperature it is independent of temperature, but when T approaches to 0, CV depend on temperature. Okay, it is directly proportional to T cube when temperature is low, and this is called Debye T cube law, and it is followed in case of insulators, okay, where no free electrons are there. Okay, and in case of metals the curve follow T law, mean to say CV is found directly proportional to T. Okay class, so this is the discussion regarding specific heat capacity of the solids. In the coming lectures we will keep in mind the experimental facts and we will discuss various theories. Okay class, thank you class for watching the lecture.